This is a lesson about radian measure, and radians are just a different unit from degrees, and it's a way to measure angles in a circle. And instead of dividing a circle, the circumference of a circle, into 360 little parts called degrees, we divided it into 2 pi parts, and 2 times pi is approximately 6.28. So we've basically divided this into 6.28 parts. So there are a little less than 6 1/3 radians here in a complete circle. So if you take a full 360 around a circle in degrees, you've gone 2 pi radians around a circle. And where this comes from is the circumference of a circle is 2 times pi times the radius. You know that from geometry. And this is a unit circle where this radius is 1. From here to here is 1. You see where we're intercepting the x-axis at 1, 0, and up here at 0, 1. So you can see we're intercepting the x and y axis with the center at 0, 0. And so when the radius is 1, this just reduces to the circumference is 2 pi. So that's where we get that. This is 2 pi all the way around the circumference of the unit circle. So from this 2 pi, if I divide both sides of this equation by 2, I get that pi is equal to 180 degrees. So this makes it really convenient for us to measure what part of a circle we're dealing with in terms of a semicircle or a whole circle. So if this is 0 radians here, or 2 pi when I've gone all the way around, and this is pi radians over at 180 degrees, then up at 90 degrees is half of pi, or pi over 2 radians. And if a semicircle is pi radians, then when I go another quarter of a circle, I've gone pi plus another half pi, or 3/2 pi, or 3 pi over 2 radians, and then all the way around, again, of course, would be, if I go all the way around, I'm at 2 pi radians. So we'll use this fact that 180 degrees equals pi radians to be able to convert between radians and degrees, back and forth either direction. Then later we'll come back and learn how to find the length in radians of an intercepted arc of a circle and the area of the sector related to that arc, and we'll study these two formulas here. So for our first example, let's come up with how the multipliers are derived for conversion. This is nothing more than like if you're converting feet to inches or something. If I start with 180 degrees is equal to pi radians, and I want to know what 1 degree is, I would divide both sides of this equation by 180 degrees, and I would get 1 degree is equal to pi over 180 degrees radians. Okay, so that if I want to go from degrees to radians, this is the multiplier I would use right here. I would multiply every degree I had by this, and the degrees you see in the numerator here and denominator would cancel out, and I would be left with pi in the numerator for radians. So this is what I want to go to in the numerator, and what I want to cancel out, what I want to convert from, is in the denominator. Now, using this same equation again, except I'll put pi radians on the left is equal to 180 degrees. If I want to know how many degrees are in 1 radian, I can divide both sides of this by pi, and then I would get, these would cancel, and I would get 1 radian is equal to 180 degrees divided by pi. And again, this is going to be the multiplier when I want to go from radians to degrees. What I want to go to is in the numerator, the units are degrees, and what I want to convert from, pi radians, is in the denominator. So in example 1, I'm supposed to convert 135 degrees into radians. So I just take 135 degrees times pi over 180 degrees equals, and so I've got this ratio of 135 degrees to 180 degrees, and the degrees cancel, times pi, and this is 135 is 4 35s, and 180 is I'm sorry, this is 3 45s, and this is 4 45s, So this simplifies to 3/4 pi, or 3 pi over 4, and that's in radians. Now going the opposite direction, instead of using this multiplier, I'm going to use the other one to convert from radians to degrees. So if I have to convert 4 pi over 5 radians to degrees, I multiply it by, I cancel the radians, and I want to end up in degrees. So when I do this, the pi's cancel, and 180 divided by 5 is 36 times 4 would be 144 degrees. So you see, what I want to end up in is in the numerator here of the multiplier. I want to end in radians, and this one I want to end in degrees. So that's, the 180 degrees is in the numerator of this multiplier. Okay, so then with both of these, we're working with pi in terms of pi. Here I left pi in terms of pi in radians. But if we wanted to, in fact, use a calculator and substitute 3.146, a decimal approximation for pi, we could express 34 degrees in radians to the nearest hundredth. So if I take 34 degrees and I multiply it by pi over 180 degrees, and then I want to put this into a calculator, then I can use, for pi, I'll substitute 3.1416, and I will get to the nearest hundredth 59 hundredths radians. So that's just expressing radians as a decimal value. Okay, and then in part B, I've got to go the other direction, express 3 radians in degrees to the nearest hundredth. So I'm going to start with 3 radians times, and the radians will go in the denominator and the degrees in the numerator. And then I'll put the 3 times 180 in the numerator, and for pi in the denominator, I'll substitute this decimal approximation, and I'll end up with, when you punch that in, you should get 171 and 9/10 degrees. Okay, so that's converting radians to degrees, and there's some standard radian and degree equivalencies, which we'll talk about in class, that are easy to derive just from understanding fractions. So moving on then, we're now going to start to talk about arc length and sector area. So if I go back to this page, the arc length, the intercepted arc of this central angle, theta, remember central angle? This is the intercepted arc. It's this unbroken piece of the circle, and it could be measured. It's hard to measure it when it's curved, but it could be measured if it was something pliable and you took it off and stretched it along a ruler. So we can find that length, and we're going to use formulas that use radians for that. And then we can also find the area of this related sector in here, which is like a piece of pie. And again, we'll use the formula for radians. So here's the two formulas, and I'm just going to show how they're derived one at a time based on the formulas you already know from geometry. So if I have, let's just take it easy here. I have 1/4 of a circle, which is 90 degrees, okay, which is also pi radians. Okay, if I want to know what fraction of the circle that is in degrees, then I would use the fraction 90 over 360. 90 degrees over 360 degrees, and that would be 1/4 of the circle. And I would have to multiply that by the formula for arc length or for sector area to find either of those things. Well, when I'm dealing in radians with this, using the radian formulas, the unit measurement of radians already gives me what part of a circle or a semicircle I'm dealing with. So let's just check this out. If I wanted to know sector length, starting off with something familiar to you from geometry in degrees, I would take the measure of this central angle in degrees, so that would be this central angle in here, which in our example is 90, but I would take that part of, or that fraction of the circle, and I would say, well, I'm going to take, in this idea, it would be like, I'm going to take 1/4 of the whole circumference. So whatever fraction this is, I multiply it by the formula for circumference, which is 2 pi r. Okay, now, instead, when we want to do this in radians, I would say S is equal to, and for the angle measure, it would just be some number of degrees in radians over 2 pi, because 2 pi is equivalent to 360. And I would multiply that by 2 pi r. Okay, well, what happens nicely when I do that is that 2 pi and 2 pi cancel, so the formula I get in radians is just that this intercepted arc length, which we call S, is the angle measure in radians times the radius of the circle. Okay, so then as far as the sector area, it's very similar. In degrees, for the sector area, I would use that same fraction, the measurement of this central angle in degrees over 360, and I would multiply this by pi r squared. Okay, but in radians, to do this, I would replace the measure of the angle in degrees with the measure of the angle in radians out of 2 pi radians, and then multiply that by pi r squared, and the pi's would cancel, and then thus reduces to the formula that the area is the measure in radians of the central angle over 2, so we'll put it 1/2 of that, times r squared. So that is where we get these two formulas, and you'll need to know those, and they're pretty easy to use. So let's look at an example of a central angle of a circle of radius 3 measures 80 degrees. So I'm just going to sketch a circle with radius 3, and an 80-degree angle wouldn't go, as far as a 90, it'd be like about so. Okay, so this is 80 degrees. So in order to use the formulas, we have to convert the 80 degrees to radians. So anyway, in this case, the radius is 3, and theta, the central angle, is 80 degrees, and we'll now convert that to radians. So so degrees to radians, I would take the 80 degrees times, and I want to cancel out degrees and end up in radians. So 80 over 180, this is 4 20s, and this is 9 20s, so this is 4/9 pi, or 4 pi over 9 radians. Okay, so I'm going to add that here. Okay, so to use the formula, the first one, for the arc length, I will start with the arc length is the central angle measure times the radius. So in this problem, it's going to be 4 pi over 9. Remember that this has to be in radians. Okay, that's what the formula assumes. So 4 pi over 9 times the radius of 3. So this will cancel to a 3 here and a 1. So we're going to get 4 pi over 3 radians. And if I want to convert that to a decimal value, I will substitute an equivalent number for pi, and this would end up being, to the nearest tenth here, 4.2 centimeters in length. This right here. Okay, so that's S. Then for the sector area, I would start with my formula. The area is 1/2 of theta times r squared. So this would be 1/2 of 4 pi over 9 times the radius of 3 squared. So 3 squared is 9, and that will cancel with this 9, and the 4 over the 2 is a 2. So I'm going to get 2 pi radians, square radians, or square, square units of centimeters here. So to put in a value for pi, and then round to the nearest tenth, this is going to be 6.28, so 6.3 square centimeters. And so that's it. That's the basics of radians.